Okay, 3, 2, 1, it's jam.
So what's up, guys? What even is light and how does it get here from outer space? There's nothing in the vastness of outer space. So how does it even travel through that space? This is one of the questions that we're going to tackle. My name's Sir Ramon and this is Science with Sir Ramon. So part of this question can be answered through the concept of electromagnetic waves. These are basically fields of energy that wobble through space. What does that mean? We're going to take that into account in this session. So what are we up to? We're going to compare the relative wavelengths of different forms of electromagnetic waves, look at some of the uses and applications of different types of waves, and explain the effects of radiation on living things and the environment. Let's get to this. So first, what are waves? Let's get a working definition. This is something I should have discussed already in like grade 7, stuff like that. But waves are basically moving pulses of energy. The matter oscillates or goes back and forth, and the energy can move on ahead of the matter. So you can see in this GIF here that the wave looks like it's moving. The actual matter, the actual slinky here, is not moving that much at all. It just moves back and forth. With transverse waves, it's up and down. With longitudinal waves, it's left and right. But again, there's no matter in outer space. There's no particles that can actually convey that energy. So how does light get the sun to here? So we have James Clerk Maxwell, and he is a guy that, so this guy Maxwell, you can see he's got a great beard going on, and he's the guy that unified the concept of electricity, magnetism, and light. So these are different concepts, different fields of study in physics before, but then along came him, he noticed that electricity and magnetism, the electric fields and magnetic fields, can have a ratio of velocity that is equal to the speed, like exactly equal down to the multiple decimal places. So he thought that can't just be a coincidence, and he figured out equations in the form of Maxwell's equations that relate all these three things into one thing. He figured out that light is basically an electromagnetic wave, and electricity fields and magnetic fields can come together into a form of wave. So very groundbreaking stuff. And so basically the concept is that instead of matter oscillating, instead of particle matter moving back and forth, it's the electric and magnetic fields that move back and forth instead. Think of it as a piece of paper or a plane. So it's like a piece of paper, and then parts of that piece of paper can oscillate. So you can see here in the lower diagram, there's two planes or two pieces of paper that oscillate against each other. Okay, and that makes up your electromagnetic wave. So there's no need for matter, it's just a form of radiation. There's no need for matter, it's just pure energy traveling and hurtling or wobbling through space. That is your electromagnetic wave. So the formal definition is that waves are waves created by vibrations between electric and a magnetic field. So what do we mean by that? Again, we look at some of the characteristics of electromagnetic waves. All right. So they have the same characteristics as usual waves. Let me just get rid of my face here. So the characteristics of usual waves, we have wavelength, we have frequency, but we have amplitude. So wavelength is basically the distance between consecutive crests and troughs. So the crest is the upper part here, and the trough is the lower part. They're basically just the highest or lowest parts of a wave. So if you take the length between those, we have the wavelength. Amplitude is the distance between the crest and the trough and the equilibrium line or the middle part of the wave. And frequency is just a number of per second that passes a certain point. Now someone asked, what is oscillate? Again, oscillate means going back and forth. So when you go back and forth, you're oscillating. Just like an electric fan, they oscillate by going left and right and left and right. So that's oscillation, going back and forth. Anyway, so note that for wave speed, all electromagnetic waves, just like what Maxwell said, they travel at the same speed as light, which is around 3 times 10 to the 8 meters per second. Very, very fast. It's the speed limit of the entire universe. So far, we haven't seen anything that travels faster than light. Technically, if you travel faster than light, that's time travel. Anyway, so the electric field and the magnetic field oscillate or move back and forth at a 90-degree angle from each other. So the E thing, the blue part, is the electric field, and the red part is the magnetic field. This means that they're perpendicular. They form an L shape. if you look at the angle between them. Now, both fields also form a 90-degree angle with the direction of the wave. What this means is that if there's the electric field, this finger, that this up and down part, and then the magnetic field, the left and right part, the oscillating, the angular point direction of the wave is like it's going outward in this direction. So we have three planes for the electromagnetic wave. So they're moving and forth in a way that makes it so that the direction of the wave is completely different from how they oscillate. So you'll see that better in the lecture video. It looks like this. There's the electric, there's the magnetic, and then the direction of the wave. Okay, so what are the different types of electromagnetic waves? Let's understand some of their characteristics. How do we classify them? So that's part of your warm-up activity as well. In your electromagnetic spectrum, your waves are usually arranged by wavelength. So that means that the radio waves, the longest wavelength, are on the far side, opposite of the shortest wavelength, which is the gamma ray. And generally, when we think of wavelength, the longer the wavelength, the lower the frequency, meaning there's less waves passing a certain point because there's longer distance between the waves. And because there's longer wavelength and lower frequency, there's lower energy. Just think of it as like if you have a piece of string or a piece of rope, if you want to have long wavelength, you just casually move it up and down. If you want shorter wavelength, you have to vigorously, violently move that string up and down in order to get this kind of pattern in your waves. All right? So again, shorter wavelength, higher energy. So let's do them in order of least energy to highest energy. So we're going to start with the longest wavelength. Okay? So the longest wavelength one is the radio wave. These have the greatest distance, these travel along the greatest distances and penetrate the most of material. So most of the atmosphere and a lot of materials are transparent to radio waves, meaning radio waves can pass right through them. Now, the most common types of radio waves that humans use are AM and FM radio waves. So AM means amplitude modulated and FM means frequency modulated, meaning you just change either the amplitude, the distance up and down, or the frequency, how often the waves hit a certain point. So you can see in this GIF, amplitude modulation makes it different in terms of and down or the volume, while frequency modulation changes the frequency or how close the waves are to each other. Okay, so here are some of the pros and cons. FM radio waves give clearer output, so that's why we have music stations that use FM radio, and it's less affected by noise and interference. So actual background noise like dogs barking and stuff, and certain materials can affect AM radio waves, but not so much FM. AM radio, on the other hand, is used for news radio notes because there's much wider coverage, especially at night, and it requires less bandwidth, meaning it's easier to fit more channels along a certain frequency, so you have more news channels. So AM radio is generally cheaper, has wider coverage, it's easier to broadcast over a larger area. So, pros and cons. Now, in the background, you can see that there's the ionosphere. And just to emphasize that the ionosphere can bounce back AM radio waves. That's part of why they have much wider coverage. Okay? So up next, after radio waves, we have the microwave. The second longest wave. Microwaves generally microwave ovens generally make that sound over there. So they carry enough frequency to have heat, but have long enough wavelengths that they go through the surface of food and can heat even the inner parts of food. So they usually heat polar molecules like water, so that's why we use microwaves in our oven. So they're also used for radar technology and communication technology. Actually, your Bluetooth is technically a form of microwave, but it's not high enough frequency to carry heat, of course. So another type of microwave radiation is cosmic microwave background radiation. So it's literally everywhere. So the Big Bang Theory, because supposedly it's the leftover energy from that Big Bang. So it was discovered by these two dudes that were calibrating a special satellite to be able to detect microwave frequency waves. And then they realized there's noise coming from literally everywhere. So they thought that doesn't make any sense. Usually you'd have noise coming from one point, like a satellite or something. But since it's coming from everywhere, they realized it must be the background of everything. Thus, microwave background was discovered. So getting even shorter with higher energy, we have infrared. So infrared has the third longest length. It carries heat very well, which allows us to use thermal imaging. So it's used in remote controls, of course, thermal imaging, thermometer guns, the things that you use so that you can take the temperature of your head in shoot to get the temperature. Uses infrared as well. And heaters in colder countries also use infrared radiation. Now, another natural source of infrared radiation is, of course, the sun. More than half of its energy is actually in the form of infrared radiation. So there is that. Okay? So infrared is very common. So getting even shorter with enough energy to actually be visible to our eyes is the visible light. It has the fourth longest wavelength, and color actually varies based on the wavelength of light. So generally, the longer wavelengths are red, and the shorter wavelengths go to the violet part. So red travels the farthest because it has very long wavelength, while violet has the highest energy because it has very short wavelength. We're going to talk more about visible light in the next topic when we talk about light itself. So now we're getting to the really short types of electromagnetic waves that can actually break down molecules. These are called ionized radiation because they can ionize or break down molecules like your DNA. So these are the dangerous types. We have ultraviolet, third shortest wavelength. So we have three distinct categories: UVA, UVB, and UVC. UVA is related to aging, so you get older faster if you get more UVA. UVB is related to sunburns and vitamin D, so you can't you have to lose some to get some. So vitamin D can only be synthesized when we're exposed to this type of radiation, but also we can get sunburn. And UVC can actually kill microscopic organisms. So generally, all of these can cause DNA damage. So if you're curing or making things have a chemical reaction based on the energy of UV radiation, if you've gone to the dentist and they've cured your like a mold or a cast if you've gotten braces, so exposing that cast to UV radiation makes it harden faster. Disinfection, so there's lots of UV disinfectants now, and making vitamin, of course. So ultraviolet radiation, not always good, not always bad. Getting even shorter makes it more hazardous, but of course there's still uses for this type of energy. So second shortest wavelength and the second most energetic is the X-ray. So X-rays have enough energy to go through thick objects. So instead of having long wavelengths, it has high energy enough to go through objects. That's why we use it to get X-ray images. They also have enough energy to damage DNA. That's why radiologists and people who don't need an X-ray are recommended to stay outside of the room. There's like a warning light bulb that you're not supposed to be in the room when an X-ray is being taken, because you're not supposed to have X-rays taken super duper often. So in medical scans like CT scans, the complicated machinery where you have to go into a tube, that gives even more doses of rays. They're also used in security, like in your airport bag scanners. So there's that. So this is one of the types of waves that can really increase the rate of cancer by around 2%. Now, a large amount of X-rays in the universe are emitted by violent stellar processes like supernovas or black holes. They emit X-rays in large quantities, and that allows us to make an X-ray map of our universe. So that gives us an idea of what the universe looks like and a snapshot of how violent our universe is. And finally, the shortest and most energetic electromagnetic wave is the gamma ray. So someone asked what happened to the doggo in infrared. In the infrared, I think. So in infrared, the doggo is having thermal imaging. In the X-rays, he swallowed keys. You can see the keys over there. So he looks happy about it. So. Anyway, so gamma rays have the shortest wavelength of all, meaning they have the most energy. They're highly penetrating, highly damaging, and they're emitted by some of the most energetic things in the universe: neutron stars, black holes, and some types of radioactive material. So there's lots of gamma rays actually produced, for example, in an atom bomb or a nuclear bomb. So some of the beneficial uses are, ironically, there's cancer treatment. So it can cause cancer, but it's also energetic enough to kill cancer cells. So sometimes there's gamma knife therapy. So they use a special laser thing that kills cancer cells while giving minimal damage to surrounding normal cells. It's also used in materials refining, so you can actually make different colors of gems using gamma rays, and irradiation, or basically killing things using gamma rays. Okay, so again, electromagnetic waves from the very inane or very mundane way of visible light to gamma rays, they all have their uses. And even though they're different wavelengths, have different types, different varying levels of energy, they all travel at the same speed. And perhaps that's something we can learn from the electromagnetic spectrum. Guys, we all have different wavelengths. Some of us don't get along with each other. Some of us have more energy. Some of us have less energy. Some of us go through life differently than others. But everyone gets to the same point in the end. We have the same speed. All right? It's not a race. Don't worry about it. You are unique in your own way, and that is fine. All right? So that's pretty much it for this topic. I'll see you guys next time.
Party's over.